Alright, so this is a demo of my version 2 of my binary to stasis chamber decoder. So this takes 6 binary inputs and breaks it out into 64 stasis chambers. So I have it right now just operating in the front row so it's easier to see. So you can see one of these gets flipped down at a time. Beautiful. So what is different about this version? Well, so redstone sucks. I didn't know how much it sucked, but apparently it's horrible for MSPT because it has like 360 block updates per piece of redstone. You can see my old version has lots and lots and lots of redstone. It's very bad, not optimized at all. So this new version, the goal was to use as little as possible. So you can see, for example, this line here is all rails, and this has to be redstone. It will not work if it's rails. And I've also tried to shorten the lines as much as possible. So before, for example, this one was going all the way across, but it actually doesn't need to. It only needs to be this long. I've shortened everything, which makes it a lot harder to understand what's going on. But I'll try to explain it. So let's start with this little example over here. So this is a simple binary converter. So you can see we have 2 levers, 2 bits, and we have 4 outputs. So that's the correct number. So you can see when I flip this, this acts as the least significant bit. This acts as the most significant bit. Amazing. So you can select all 4. But how does this work? Well, let's disable this one for a second and just look at this. So you can see that for this 1 bit, we have 2 lines, and one is on and one is off. And you can see as we switch this, these 2 turn on, and we switch it back, these 2 turn on. So you can see this output, we're either choosing this set of 2 lights or this set of 2 lights. But this first bit doesn't distinguish which one of these 2 lights we're selecting. So if we disable this one, we'll see the opposite is happening. So this one doesn't distinguish between this group and this group, but it distinguishes between the 2 elements of each group. So you can see as I flip this, it does that. Amazing. So let's look at this torch pattern here. So you can see with this first one, there's 4 inputs, so we take that number, divide it by 2, so we have 2 torches here. And then this next one, we have this original input, and we divide by 2 again, so we get 1. So we get, let's look at this pattern. So with 8 bits, we get 4, so we get 4 in a row of on and 4 in a row of off, so this would be like torches here and no torches here. And the second one, we get 2 and 2. And this last one, we just get a ton of 1s. So this is the basis of how this works with the decoding. So the one we're specifically selecting stays off. Additional note before we continue, we are not just using a redstone torch like this. Instead, what I'm doing is essentially I have a rail line up here. I can just get some rails to show you. And observer, okay. So we have a line like this, and let's say if we're selecting these 2, then we'd have 2 observers here, and then in the next row we would have 2 observers here. So we can observe this exact thing I'm describing over on the actual thing. So you can see we have 2 pairs of binary decoders. So you can see we have 6 of these, and each of these is a pair, and each one of these is 2 bits. So you can imagine as I do this, one of these goes down, one goes up, and only one of these gets powered at a time, just like how we did that torch thing over there to select them. Again, we're not powering this continuously, we're just giving it a pulse. So if we look at this graph here, we can see that the first iteration will have 4 in a row, then 4 of gap. So you can see we have 1, 2, 3, 4 in a row. Then if we continue this line, there's a gap, so it doesn't actually transmit to this. And if we were to flip this, it would go to the other one. And the other one is the inverse. So you can see we have 1, 2, 3, 4, and then we have 4 gap here. And then we just continue the pattern, so we get to 2 in a row. So 1, 2, 1, 2, and then just every other, like that. So we also have the same thing over here. So we end up with 16 redstone lines here, and each of them only has one of them that doesn't turn off. So we could set up a really stupid thing and have this be completely linear and decode these two inputs, or we could make use of 3D space and make it a grid. So we have a 2-dimensional pattern. So to do that, we need to have some sort of selection method that goes in this direction. And we also need some sort of selection method that goes in this other direction. So let's just call this left-right axis X, and this like forward-back axis Y. So you can see that both of these lines start out as being an x-axis, which is not what we want, because we want an x and a y. So this, so the light gray circuit weaves in between the gray circuit and goes to the black circuit, and this black circuit is our y lines, like this. You can see they're running perpendicular to the ones above it, and we send the signals through it, like in between them, using observers. And you can see this is sort of a diagonal, so for example, this line here, oh boy, it goes down and triggers this one, which then extends this way. You can see it continues diagonally all the way across. So we've got an x and a y. That's great and all, but how do we decode this x and y into our output? Well, this is a little bit of an issue. So let's just give it a test here. So if I run this, well, oh right, need a. This is probably broken. 1 second. I need to repair this. Right, and then we will disconnect this. Okay, so I will give this one pulse at the top. You can see that all of these extend here, except for the one we selected. So essentially, each one of these pistons is acting as an AND gate. So we have an AND gate between this line and this line, and we have an AND gate between this one and this one in a grid. But the AND gate is the opposite of what we want. So let's think about this. How can we invert this signal? Well, you can see that this is extending onto a torch, and that inverts it. But on its own, that's not really what we want. Oh my gosh, that is not what I meant to do. Okay. Oh my god, I did it again. Okay. There we go. Because it's flipping everything except the one we want. So let's first imagine. Let's just imagine it at this example where it's a lot easier to see what's going on. So we have our pulse that from the decoder, and it extends this here. You can see that it turns this off, which is not what we want. So we also have this additional line here. So this line here is interesting because it actually controls every single piston. So this controls all of them. And what's interesting is that this sends a 1-tick pulse to all these pistons, but it's offset from the pulse this decoder gives by 1 game tick, or half a redstone tick. So I have this shown here. So you can see we're sending it 2 1-tick pulses, and they're both 1-tick pulse, but they're offset by 1 game tick. So this is long enough so the piston holds onto the block, but not so long that it actually turns this torch off. So if you give a redstone torch a 1-tick pulse, it will not turn off. But the problem is, if you give this piston here a 2-tick pulse, it actually pulses it for long enough to turn this off. If you give it a 1.5 game tick pulse, you can see it extends, and this redstone turns on, but the torch never turns off. So now let's look at the opposite. Remember, this offset grid here by 1 game tick applies to every piston. So now we're going to imagine we've selected the one we want by not giving it the pulse from the decoder. So now, when we do this, well, look at that. It's not 1.5 ticks anymore. It's just 1. So the block stays extended, and if you pulse it again, it retracts. So that's exactly what's going on here. So let me, oh, okay. Let me just get this running so you can look at this. Wait, I need to turn this off and do this. Alright. Why is it not in the first row? What the hell? 1 second. Technical difficulties. Oh. Yes, I never flipped that back. Okay. So you can see every single one we don't want, every single piston we don't want gets 2 1.5 tick pulses, or 3 game tick pulses, and each time it extends, it turns on this dust, but it turns it on for a short enough period of time that this torch does not flip state. But the one that we do want stays down because it's only receiving a 1-tick pulse. And we immediately pulse it again to make it pull back up, because this really doesn't need to stay down for very long. I could adjust the timings and have this stay down for as long as I want. I found that for enderpearl stasis chambers, really all you need is 4 redstone ticks, and it's very convenient. So let's just look a little bit at the optimizations of this and compare it to the original. So compared to the original, this is less compact. So it is 2 blocks deeper. However, it's a lot better in that this original one, you can see that the stasis chambers are staggered in height, whereas in this one they're all the same height. Oh my gosh. Also, this is using lots and lots of redstone. Additionally, there's a lot of stuff that can be optimized with this. So, for example, like these rails and even like all of this is not necessary for it to function. I just left them in because it was much easier to understand what was happening while I was debugging it. It was a nightmare to debug this thing, by the way. Yeah, so lots of these paths can be shortened. For example, this one over here, it has to go to this to make that 90-degree conversion, but all of this is completely unnecessary and just adds lots and lots of lag. So we've shortened all the pathways to the minimum, and everywhere we can, we've replaced it with these rails. So it's a little bit difficult because, actually these are not necessary. I don't know why these are still here. Redstone can go 16 blocks. Like technically it's 15, but practically for what I'm doing it's 16, which basically means across this entire thing I can power it in the middle, or I can power it at the very end, and I know that it's still going to be an active signal at the other end. The same can't be said with the rails, which created a problem that required some creative solutions. So rails, I don't actually know the exact number, but it does not go to 16. It's a lot less, which is a problem. So let's just look at this one example here. So we have this line here. It goes all the way across, and it's being powered by these 3 observers. So if we were to have this be rails, and it's just getting a pulse from this observer, well, that's going to be an issue because that actually doesn't extend all the way over here, and at this point we're actually using the signal and using it to decode this piston here. So to solve that problem, I actually put in the minimum amount of redstone. So you have just enough redstone, you can see it extends far enough for this to work. And that probably broke everything, but that's okay. I know how to fix this thing. So you can see all of these rows, they have this redstone in this area. And then when we do this 90-degree turn, I can't even get inside this thing, it's so dense. Yeah, so like right here you can see we have redstone at the end, and if we go try to get somewhere in the middle, so like directly in the middle we don't need any redstone, but a little bit offset from the middle we need like 2 pieces here, or one piece here. Yeah, I've removed as much redstone as possible. So, let me know what you think. I think this might be able to be compacted. I know that there's probably some way to do it, but I can't think of a way to make this area be more compact. This top thing here, we have compacted a lot. This is really bulky and just a proof of concept. From here all the way to this level here, I think is the minimum layers, because you have to have one block gap between each of these. You have to have one layer for the decoder to our 2 lines, so that's that, and then it has to turn 90 degrees so we get our cross grid. Yeah, at this point though, the decoding circuitry could be smaller. Excited to see if anyone else wants to compact this, or what to do with the concept. I'm pretty excited with the progress so far. I'll see you later.